All right, let's get started here. Good morning, everyone. So today we're going to be talking about coordinate reference systems. And I do believe so there is going to be a lecture for today, and then we're going to be using some of these concepts in the next class, next Monday, where I'm going to change a little bit the order of things here on the schedule, just to let you know. So today I believe we're going to be able to cover this topic here of coordinate reference systems. And then I'm gonna move this digitizing field boundary and retrieving elevation to after the USDA NAS data exercises. So next Monday, we're gonna be working, starting with the topics of geospatial data types and USDA NAS data. That's gonna be what we're gonna be doing on Monday. All right, so for today, again, it's a lecture. The slides are posted on the website. It is in HTML format, so you're welcome to follow along from there. I'm just going to launch that on my side. And remember, you can always download the slides as PDF and take notes. On my side, if I click the letter E on my keyboard, this makes the slides as a continuous scroll, and then you can download this, save as a PDF from your browser. Okay, so coordinate reference systems. This is going to be a very important topic for us because, as you probably know and expect, we're going to be using with a lot of geospatial data, and all of those geospatial data layers need to have a coordinate reference system so we know where they are in place in space, and can use that information to match different layers, and make sure that they're all overlapping when they should be overlapping. I just want to do a quick acknowledgement here that some of the materials of this lecture were based on previous slides from Dr. George Velides, another professor at Precision Ag here at UGA, and also these two ebooks. These are some good resources that I have on my side, and I do encourage you that if you're having issues with geospatial data, especially in R, these are really good resources. So Geocomputation with R ebook, this is the hyperlink, you can click on it. An Intro to Spatial Data Programming with our ebook as well. Okay, so for today, we're going to be talking about what is a coordinate reference system, the difference between geographic and projected coordinate reference systems, why should you care about that, what are some of the most common coordinate reference systems used. We're going to be then talking about EPSG codes. If you're not familiar with this is going to be an important concept for you for this class and also any other geospatial exercise you do. And that's what we have as learning outcomes for today. Okay, so to begin with, what is a coordinate reference system? Let me see if anyone can help me out here. Just, if you have any thoughts, any ideas, doesn't have to be the correct, but just what comes to your mind when you think of a coordinate reference system?
So basically, it would be something related to coordinates present on Earth, like longitude and latitude, based upon which we can identify location precisely.
Okay, nice. That's a great way of thinking of it. Thanks, Kumar. That's very accurate, right? So it is a system that we're going to use to be able to place and locate something in space, right? So any geospatial data layer that we use, so normally we're in this course, we're going to be using mostly vector and raster geospatial data types. And these types of layers require a CRS to be correctly placed in space. So a CRS, let me just do this here. A CRS is going to define how the spatial elements of that data relate to the surface of the Earth. Well, that's the most common one to refer to, but it could also be to other different bodies. It doesn't have to be just the Earth. If you're talking about, I don't know, different planets, you would have their own CRS, of course. And one very important distinction here, I do want you to pay attention to this, and if you are not familiar with it yet, I do want you to become familiar, is that there are two main categories of CRSs. So one of them would be geographic, the other one would be projected. And all CRSs, regardless of if it is geographic or projected, rely on a datum or datum. What is before we get more into CRS, let's just define what is a datum. So a datum is going to contain information on what ellipsoid is being used by that CRS to precise the relationship between the coordinates and location on the Earth's surface. And there are two main types of datums. One is geocentric, the other one is local. So I have this figure here. I will zoom in just to give you some idea. So a geocentric datum, so the first type here, is what you see on this black line. So you see that it tries to approximate the Earth shape equally across the whole globe, which means that it's not going to be the best one to define the specific location anywhere in the world, but it's going to be a good, I guess, average, if you want to think of it that way, of precision in locating something on Earth across the whole globe. In contrast to a geocentric datum, there is a local datum. So a local datum is actually developed for there are different local datums that are developed for specific regions of the world, and they do match that region very well. They work very poorly outside of that region. So here we see a local datum that is approximating the topography of, or I guess the shape of the Earth on this very specific place on Earth. So whatever this is, I don't know, it looks like it would be maybe somewhere, I don't know, in Russia perhaps, or China, I'm not sure. But anyways, in this exact location, in this example here, this local datum works very precisely for that location on Earth, but it has very large errors everywhere else, right? So this would be a main difference between the datum. So a geocentric datum, it kind of does an average job everywhere. A local datum does a very good job in a specific place and a very poor job elsewhere. So let's say if you're in a different place of the world, you would use a different local datum that fits that part of the world very well, but it fits other places poorly. With that, let's get into what is a geographic coordinate reference system. So the geographic coordinate reference systems normally use a geocentric datum. So that would be the one that we saw that does an okay job everywhere, but is not the best for any given location. And uses angular measurement units. So Kumar was saying longitude and latitude. If we're talking about longitude and latitude, those are is a degree measurement. So it is an angular measurement, and it's used on geographic coordinate reference systems to locate something in space. You know, I'm sure you probably have heard about this already, but just a very quick refresher here is that longitude is the location east-west, whereas latitude is the location north-south direction. And a very popular example of this is called WGS 84. So I'm sure you came across this already. WGS 84 is perhaps the most common CRS altogether, not just geographic, used in the world, including in agriculture, because a lot of the equipment that we use in farming equipment, or any GPS using farming equipment, most of the time is going to be collecting data in WGS 84. If you use your phone to locate yourself, to look for directions for whatever, it's going to be WGS 84. This is the most popular one, and most likely, if you're bringing a data layer into any software, including R, that native CRS is probably going to be WGS 84. So here, let me just zoom in. This is just an example of how the world is split. If you're talking about a geographic CRS, in this case here, WGS 84. So we have degrees of longitude going east-west and degrees of latitude going north-south. And then we have the prime meridian and the equator as the two main reference points of this type of reference system. Okay, now the other example here that I also want you to be familiar with, it's going to be important for us throughout this course, is a projected coordinate reference system. So that normally uses a local datum. So as you were talking about, there is the geocentric datum, there's a local datum. A local datum, again, is going to do a very good job of locating something on Earth for that specific location, but it's going to do poorly for other locations if you use the same one. Of course, you're going to have multiple local datums across the world where each one of them fits well that part of the world, but it should be using that local datum if you want projected CRS for that part of the world. So the issue here, I guess, is that a local datum in a projected coordinate reference system needs to convert that three-dimensional surface of the Earth into a plane, right? And this plane is what we use then easting and northing, or X and Y coordinates. So now we do not have degrees. It's not an angular measurement anymore. It is a linear measurement unit. For example, meters. It could be feet. It could be anything else that is a linear measurement unit. So it is not angular anymore. It is a measure of actual distance. And a very popular example here, I'm sure you heard about this already, is universal transverse Mercator. We refer to this most commonly as UTM. All right, so let's just take a moment here and talk about UTM itself. So UTM divides the Earth into 60 zones, and each one of those zones would represent about 6 degrees of longitude and width. Each one of these zones is going to basically cut the globe. So imagine now, instead of having a globe, we have a plane of the whole world, where the whole world is now divided into the 60 zones going north-south. So cutting all the way from the northmost part of the map to the southmost part of the map. So you're going to have 60 of these divisions. And because it is now, so imagine that each one of those 60 divisions are going to have their own local UTM projection, in a way that, because you're keeping only a sliver of the world and considering a CRS for that only, is going to be very precise for that location, right? So we have very little distortion, and is really one of the most used when we need to know actual distances and have that as an important feature. Also, another way of kind of sub-segment this 60 zones is by using the equator line as our divider. So we would have, let's say, zone 1 starting on one side, zone 60 starting on the other side, going in this direction, the east-west direction. Then you have the equator cutting them. So let's say zone 1 is going to have zone 1 north, zone 1 south. Every zone here is going to have a zone north and a zone south part of that. So this is just how that looks like for the Earth, right? So we have, notice how now I'm not showing you a globe, right? This is not a geographic, it's not in angles. It is a plane where we're basically using a metric unit, where for each one of those zones, we have a different coordinate reference system that has its center points specific for each one of those divisions, which is what helps it to be more precise. Instead of just using the equator as the main point source and the prime meridian as the main source, now it has a main source region for each one of these divisions. And again, that's what allows it to be more precise. So we see here going from 1 to 60, and it's not showing here the north or south, but imagine that if you have the equator line here, all the zones that are, or all the cells that end up above the equator would be denominated that zone number in north, and if it's below, it'd be that zone number in south. So 1 north, 1 south, and so on. What about UTM in the USA? So here in the US, we basically have, at least on the conterminous US states, we have the zones ranging from 10 to 19. Here in Georgia specifically, Georgia is cut through, and you can find places in Georgia that are either on zone 16 north or 17 north. And north, again, because we are north of the equator line. But as far as zone number goes, here in Georgia, we're either going to be within a 16 or 17 zone in terms of UTM zones. Okay, so I'm showing you here a couple of examples, or maybe, I mean, it's the same location, but projected in geographic and or with a geographic CRS compared to a projected CRS. So geographic versus projected. And I just want to give you 1 second here to see if you can spot, you know, something here, a difference here, or maybe a couple of differences. See, Sundes, what do you see here? What do you spot?
I think the data may have been little distorted and strange.
On the, so you think one of them is a little bit distorted?
Yeah.
Which one of them you think is distorted?
Right.
The one on the right? Yeah, so it's a little bit angled, right? Yeah, I agree. Anyone online wanted to chime in?
Looks like one is angular and one is metric.
And how do you know that?
We can see the labels around. One is like an angle of angles and one is just numbers.
Yes, great, great. That's exactly the one of the points here as well. So yeah, a couple points, right? So it looks like, okay, well, let's begin by what Vinicius just said. So the one on the left here has degrees as the units. If you have a degree measurement, this is probably going to be geographic, and it is a geographic coordinate reference system. We also see that it has latitude and longitude on the axis, right? Whereas the one on the right, we see it says X and Y, and even though it doesn't give us the units here, but I can tell you that these are units of distance based on the origin of this specific UTM zone here. So this is just the distance, the northing and easting distances from that meridian of that specific, or not meridian, I'm sorry, from that point source origin of this specific zone here of UTM. It's kind of interesting as well because as Sundes pointed, it looks like the one on the right is, so he used the word distorted. And I want to use a different word, I guess. I want to use, it looks like it moved a little bit, right? It's kind of like at an angle, sort of. And really, you know, this is going to happen, right? So I want to call your attention here because, again, if you're using a geographic CRS, some of your layers have a geographic CRS. Let's say you're using WGS 84 and others are in a projected CRS. You could run into issues depending where your field is, because if these were 2 different layers, so let's say one was soil type, the other one was, I don't know, yield or let's say elevation. But I mean, even though those are not what is showing the map, but let's just think about that. If you're using 2 different layers for the same field and they're not in the same CRS, they're not going to match in space. You can imagine how if we would try to, I guess, overlap these 2 maps here, they would probably have some distortions. It's not going to be completely overlapping because even though it's the same place on Earth, but they're being shown and used using different CRSs. And also, you know, what we see here as far as being a distortion is actually, I guess, you know, we can think of it as a distortion, but it's really just this map here would place that location more precisely on Earth. So it's, you know, it's not a distortion in a bad way. It's more that it's representing more of where that is actually in space as compared to WGS 84, since, you know, that has a larger error. It is a good fit on average for the whole world, but it's not the most precise for any given place. Awesome. So this is another example here. I do have the labels there of what is the coordinate reference system. So this first one here is WGS 84, and you can kind of see that's kind of like, it's kind of squared, right? It kind of fits as a square, whereas this other one here that is the US National Atlas is kind of a little bit more following the actual shape of the US, right? Again, we can look at the units, right? So we see here that WGS84 is in degree units of longitude and latitude. And on the other side here, even though it doesn't give us the exact unit here, but you know, it doesn't have a degree on it. So it's most likely a distance measure of some sort. And again, just to call your attention that, you know, you need to have your layers under the same CRS if you want to use them together for any given place. So they match in space. Here you can also imagine that if I would try to overlap these two maps, even though maybe they would kind of overlap well in the middle, but they would not overlap well on the outer sides of the country here, as you can kind of tell by just the way they look in this map. Okay, so CRS is used to place something in space. We have two main categories of geographic and projected. But now whenever it comes to software, and this doesn't have to be R, it could be Python, it could be ArcGIS, it could be QGIS, whatever software you use that uses geospatial data, you're gonna need to refer to a CRS if you want to change it, either assign it to a layer or change it to something else. So that means we have to have a way to refer to them. There are, you know, maybe a few different ways of referring, or more than a few, but I'm going to show you a few different ways that you can refer to some of them. So it could be, you know, as simple as you telling someone it is in long lat coordinates. That, because WGS is one of the most popular, one of the most widely used CRSs, you know, if you just say long lat, you know, another person that works in geospatial analysis will probably know what you mean. Software is not going to know what you mean if you just say long lat. There used to be, and perhaps you're still going to see this, especially if you Google when you're looking for help on geospatial data, there used to be this, or I'm sorry, there still is, but it's less popular these days, these proj4 strings that are also known as proj string that would give you something like this. So this text is what you would use in R or any geospatial software when you're trying to refer to, in this case, WGS84. And then each one of the different CRSs that you have available, and there are many of them, like I don't even know how many, but probably thousands. You would use something like this where you would use this notation here that you're seeing right here as an example. So this would be a proj4 string, and at least I used to use these in R in the past. I don't use this anymore because this is actually a very short example of a proj4 string. They can be more complex than this, and then it's really difficult for you to know exactly how to refer to one. You really have to Google it, find the source, copy and paste, and so on, which makes it a little bit more, you know, complicated, I guess. The third option here is to use what I want to introduce to you as EPSG code. So an EPSG code follows the syntax here where the authority is basically EPSG. So that's the entity that basically standardized these CRSs, and then you give it the code. So the code here for WGS84, you're going to see this code a lot. So you don't have to memorize this from today. And my class is not about memorizing things, but I do want you to remember in a way that this is the only or this is the most used EPSG code that you're going to have and see in your data analysis, any geospatial analysis. 4326 is the code, the EPSG code for WGS84. So now instead of coming here and giving software this whole string, I can just come here and say 4326, it knows what I mean. However, all these previous three ways that I described to you, they're, you know, different ways of referring to it, but none of them is completely thorough as far as all the information that you could provide about that specific CRS. There is one last way of referring to a CRS that's called a WKT description. This is an acronym that I don't quite remember what that means now, but it's really, it can kind of follow a similar idea of a proj4 string, but it's just a lot longer, maybe like 15, 20 lines of code would be a WKT description. So it is the most thorough, but it is still long. So it's not very easy to refer to it. And I'm just exposing you to all these, especially the last three ones, because you may come across these as you Google things. So I want you to be aware. And for the most part, and for this class especially, we're going to be using EPSG codes to refer to different CRSs. Okay, so why is EPSG codes preferable? So it is machine readable, meaning that your software, your geospatial software, is going to know what you mean when you give it a given EPSG code to refer to a CRS. It is short and easy to remember and reference because it is just a number, right? It is normally is between, I don't know, 4 and 6, maybe digits number, which is a lot easier to remember than a whole string with many different characters, or maybe even you know, something longer than that, like the WKT approach. It's easily findable online on this EPSG website. So this is a hyperlink. If you are following on the HTML, you can click on this. It's going to take you to this epsg.io website. You can either come here and look for, so let's say you bring a layer in your analysis that already comes with a given EPSG. So let's say it's a crazy number you've never heard of. It's not 4326, and you just want to know what that is and what type of CRS that is. You would come here and just type that number. It will look for that for you. In this case, I just typed the one for WGS84. So it's giving me this information here. I can click on it. And get all this information about that specific CRS in this case. So here is, I think is a good example as well. So here we have the description of 3 WKT. So that means well-known text. 3 descriptions of WKT for WGS84. So this would be one of them. Notice how it is longer. It has more information. So again, it is the most thorough and precise way of referring to it, but it's not the simplest one because it has a lot of information there. This is another example here if you want to use WKT2, and then there is an Esri. So Esri is the company that created ArcGIS and many of the things that we use in geospatial analysis, like shapefile concept and so on. There is one for Esri as well. So you see how WKT is going to be more complex than just given 4326. Another way you can use this website is to come here and look for a place on Earth, right? So you can come here and say, I don't know, Georgia, USA. And it will give you a list of different types of CRSs that include Georgia, the state of Georgia in the US. So you can really explore them, look at what's the unit, what type of projection it's using, and so on. So really, I wanted to show you this because you know where to look for this information in case you ever need it, and you can reference that very easily here. All right, so now why should you care about CRS? Like, why can I just bring in my layers into a geospatial software and just work with that, however way it comes to me? Well, the reason here is because we want things to be properly aligned, right? So this is just one example where we have multiple layers for a given field. So we have a watershed, slope, soils, land use, and other things here. So the goal really is that we can align these layers in space so we can extract information. We can combine these layers in different ways. We can create management zones. For all that to happen, they have to align. And for them to align, they have to have the same CRS. Okay, and now why should you care if it is geographic or projected? Can I just work with WGS84? I mean, most of my layers are going to come with that CRS anyways. Why can I just not use geographic for everything? So first off, knowing what CRS your data is in and making sure that they match the same CRS is going to have very important consequences for how in this case R, but really any geospatial software is going to handle those spatial and geometry operations. With time, so R has evolved as far as what packages are used to handle vector data and handle raster data, which again are the two most common types of geospatial data we're going to have in this course. And R has become better at, let's say, if you give, so let's say you're doing some function in R that it's distance based. So it would be best fit if you gave it a projected CRS in meters rather than an angular CRS in degrees. So if you give it a projected CRS in meters, is going to do a very good job of doing a distance-based operation. Like, for example, calculating the distance between 2 points, making a buffer around something, or something else related to distances. However, if you give it a geographic CRS and ask for those types of operations, it would try to on the go, on the fly, adjust that geographic to project it and then give you a result. So it's going to try to accommodate that, but it's not going to do the best job it could. So it's not foolproof. And I just want to show you here one example. So I have here 3 plots where it's going to be 3 situations. And I do want you to be familiar with these 3 situations because you will run into this for sure in this course and for sure in any other data analysis, geospatial data analysis you do. So the one right in the middle here, it is a projected CRS. So all of them are the same point in space, right? So for the first one in the, or I'm sorry, not the first one on the left, but the one in the middle here that I want to call your attention first is one that's using a projected CRS in meters. And then you see a point in all of them. And then I ask for a buffer. This is something is a very common operation, geospatial data, is to create a buffer around something. The circle around this dot here that you see is that buffer. If I ask for a buffer, which is a distance-based operation, you see how that circle is very smooth and even, and the radius is consistent, right? We have a circle. And that's because, number one, this layer has a CRS, and that CRS is projected. So has CRS, it is projected. Another example here is on the right, where in this case here, this layer did not have a CRS assigned to it. So the CRS was NA, not available. So a software, when doing a distance-based operation, is going to try to accommodate for that, but you can clearly see that this is an ellipsoid. It's not a circle, right? And if you want a buffer, normally we're looking for circles. So this case on the right is also not the best one, and this would be a case where the CRS is unknown. When does that happen? That can happen in a few cases. If you ever use shapefile types of files in any geographic information system, you're probably aware that even though there is a .shp file that is an actual shapefile, but you also need to bring in with that maybe other 5 to 6 different files that accompany that shapefile that gives the context of that to your software, your GIS software. What happens is one of those files is the projection, is the CRS. If you don't have that, or maybe you ask someone, hey, can you send me the shape file or the field boundary for my trial this year? And they send you an SHP file only. First off, that's not going to even open on your software because that's not how it works. You need all those accompanying files to come with it. And if other of those accompanying files come with it, but the CRS is not one of them, you may still be able to open that shapefile into a software, but when it comes in, that software is not going to know what is the CRS of this shapefile. And that's what the case that we see here on the right. Now, on the left side, so the first spot that you see here, it is a case where we know the CRS, and the CRS is geographic, so it's WGS 84. And then when I ask for that buffer, see how this line, it still makes a buffer for us, but see how both of those lines are not a circle, right? They're kind of like a jigsaw type of line, which is not what we want. So this is a GIS software trying to do on the fly adjustment of your geographic CRS to project it and give you something. So it will give you something, but it's not going to be as precise as if that CRS was changed to a projected CRS instead of geographic. So the bottom line here is that we need to have geospatial layers within a project to have the same CRS. So if you are, working with multiple layers, which we will be doing in this course, all from the same field, we want them to have the same CRS so they all match in space, and we can do things like management zone creation. If the CRS is absent, or when you import that file and you inspect it, it says CRS equals to an A, we need to first set the CRS of that layer. And it has to be the original CRS of what was used when that layer was collected. So what I've seen in the past happening is, let's say I bring in this shapefile, this maybe is a field boundary, and it does not have a CRS. So the CRS is NA. It still has the unit, so it can kind of look at the units and kind of make sense that, those units are angular and not metrics. So it kind of gives you a hint, or maybe you can go back to where you got this data or the person that sent you and ask, hey, what was the CRS that was used? And they can tell you. Again, most of the time, a good guess is WGS84, but that is not always the case. So let's say that I bring this in, it has no CRS known, and I'm guessing it is WGS84. The first thing you have to do is set that CRS to WGS84, even if WGS84 is not the CRS you want to use this layer under. The reason for this is what I've seen sometimes people do is they bring a layer that does not have a set CRS, and let's say it was WGS84, but instead of assigning WGS84 first and then transforming to a projected CRS, they would just assign the projected CRS right off the bat. The software is not gonna yell at you, it's gonna allow you to do it. But but now it's taking these units that are degrees and you're saying, these are not degrees, this is metric, when it's actually not. So when you plot that shapefile on the Earth, you're gonna end up somewhere in the middle of the ocean or maybe in Antarctica. That's very common. So remember that if your layer comes in with a CRS, great, you can already transform that to something else if you need to. If it comes with CRS equals to an A, first, you have to set the CRS to what was used to collect the data and then transform to a different one if you need to. And then, I guess, just rephrasing that last part, if the CRS is present, but it's not the one that you want to use. So you bring in, it knows that the CRS is WGS84, but I want this under UTM. I don't have to set the WGS84. I can just go ahead and transform that to the one that I want. In this case, in this example, would be UTM. And this piece of advice here that goes back to the previous figure I showed you, if you are conducting distance-based operations, like calculating a distance from 2 points, or maybe doing a buffer, other things like that, interpolation, it is preferable that you have a projected CRS. So it should be in meters and not in degrees. So just recapping here, the CRS is going to set the spatial location of an object so we know where in space that is. There are two major categories of CRSs. One is geographic, one is projected. Regardless of which one you use, you want to make sure your layers are all having the same CRS so they align in space. And if you're performing distance-based operations, we should be preferring to use a projected CRS, even if our layers come as geographic, but we should transform them to projected before doing these operations. And just some, this, you're going to see this as we start coding, I guess, next Monday, but some common CRS that we use is, again, in the case of geographic CRS, WGS84 is the most common one. And the EPSG code for that is 4326. This is also a hyperlink. If you click on this, it's going to take you to that EPSG website for the full description of this CRS. And the other one that's also going to be used a lot in this class is, in the case of projected CRSs, is going to be the UTM zone 17 north. And that's because the field we're going to be working with is in zone 17, and we are in the northern hemisphere, so that's the north there. Perhaps if you work with other data from Georgia or even from other states, especially, you may be in a different zone. So this E EPSG 32617 is only for UTM Zone 17 North. If your field is in Georgia but is on the Zone 16, your code is going to be different. It's going to be a different CRS, like we talked about. That all of these UTM zones, each one of them have their own projection, in this case, a different EPSG. So just to be aware of that. Okay, so that's all that I had as far as lecture, introducing you to CRS and making sure we're all on the same page. Let me open the floor for questions. Anyone has any questions? All right, so I don't,
I do, but
go ahead.
I had a question, but it wasn't related to what we did today. It was going back to the other question that I asked the other day on the GitHub thing. But I can wait till like later to ask that.
Yeah, well, you can go ahead and ask that now, because yeah. You can go ahead, Clint.
Okay, so the issue that I ran into, I realized that I know it was case sensitive, and I realized I had that a capital letter in there instead of the lowercase.
Mhm.
And then when I tried to rerun it, it gave me an error and said that the object soy K1 was not found.
Okay. So I do want to talk more about the assignment responses and what I got from you all, the issues that you all reported to have. I think I'm probably going to do this next week, but just a quick recap is because I saw what you're mentioning a few times, you know, from different people. So I just want to make sure that whenever it says that an object doesn't exist, what it's telling you is that you have not run yet the code that creates that object. So if you were to look on your environment on the right, you would not see soy K1 there. So really all you would have to do is just run the chunk that creates soy K1 and then, you know, going through the code. So remember that we were doing all these intermediary objects, right? And for the next one to work, it relies on the previous one to have already been ran and created. So that's what was happening in this case specifically.
So, so if you go out of the session of our studio and then come back, you have to run it. Because the issue that I was having is that I never left, and I'm in Rock Eagle right now. We don't have internet. So when I came back, I thought it was still in the session, and I guess the session was completely out, right? And then I had to rerun it. But in my mind, I was like, it's still there. I never left the session. So
Yeah.
maybe, so I guess after inactivity, it logged off of the session.
So it doesn't have like a login or log off system. So it's not by that. The way that it kind of resets things is if you close your RStudio window and then you reopen that project later. So when you reopen it again, that's when it comes blank. And that's not, you know, I heard this sentence once I thought was really nice. It's not a bug, it's a feature. We want it to be that way because we don't want to be closing RStudio, reopening, and having the objects it created on a different day to come back today. Because what could happen is, let's say today you're doing soy K1 and do something to it, and then you leave it there. And then tomorrow you come and you change the code for soy K1, but you forgot to rerun it. So you think soy K1 that's up there has the changes you made, but actually it doesn't. And that creates all sorts of confusion. So we don't want ghosts of our objects, because we can always reproduce the objects by having the code and the data, right? And that's what we want to save. We do not want to save the objects themselves. So yeah, it is not a bug, it's a feature that it doesn't save from one to the next. So I just want to, we can definitely talk more about I want to talk more about the assignment and show you some of I got maybe two different types of answers. Just one of them is correct. I want to talk about them in next week, so we can really go through it, think through it together, see what happened, understand some of the mistakes, understand some of the code errors, right? So this, especially in the beginning, I want to take this time to go through any troubleshooting because I think that's a really great lesson or teaching moment, not just for the person that's struggling, but for everyone. So I think those are very important. I do need to cut this short now because the class only goes till 10 and I have a quiz for you all. So let me get to that right here. So if you go on UGA ELC, so I have a quiz that has 5 questions. It is 5 questions, but they're really straightforward, just like drag and drop, true or false. So it's pretty straightforward. You should be able to complete them now. Let me make it visible so you can all start with that. Okay, so I just made it visible. It's called Quiz 1 CRS. It has 5 questions. Please go ahead and answer them. My goal here is that you don't look at the material. Again, my goal is to see how much you are able to understand from what we talked about today. So do not use the material. You don't have to get everything right to get 100%. Don't worry about your grade. I just want to assess your learning on a very slow or low stakes way. So please go ahead and complete that. While we do it, I also want to open the GitHub for attendance. So after you complete the quiz, go ahead and claim your attendance.
Dr. Bastos, there is another way to open the quiz because I'm not registered in the classes yet because I have votes. I'm not in the United States. There is other way to open.
Yeah, I don't think so. So let me. Yeah, I guess I did not remember that point. Let me just create this issue here, attendance, and then I'll think about your case. So I think what I'll do is I'm gonna take, let me open this up and I'll take a screenshot. Let me see if I can see this preview. Okay, I'm gonna take a screenshot and send you, and then you can kind of just write even on an email, you can just write back your answers to me. It doesn't have to be, you don't have to use, I mean, I don't know. If you want to write directly on the screenshot, you can as well. Is it going to be up to you? But yeah, whichever way you can do it to answer, you can just send me your answers then. All right, Vinicius, I just shared the questions through your email. So yeah, I mean, I do ask that that everyone completes this before you leave the class today. The class ends at 10. If you have something going on afterwards, I do ask that you finish before then. Also remember to claim your attendance. And Vinicius, in your case, before you disconnect, I guess, submit your answers by email.
Sounds good. I'm ready to receive your NA. Okay, I got it. I'm gonna do it right now.
All right, well, I'm gonna stop the recording here, but I'll keep online, in case anyone has any questions online. And then we can take another 5 minutes to wrap up.